Thank you very much for having me, and thank you for the introduction. So, as Fredrik mentioned, I did my PhD here in Chalmers in the Department of Physics, right upstairs, and I focused on AI for single molecule microscopy, nanoplasmonic spectroscopy, and mass spectrometry, essentially. And after my PhD studies, that was done about a year ago, I joined my company, Iflai, that I co-founded together with a couple of colleagues. So who are we? You might recognize a couple of faces here because there's more people from Chair. But we together worked essentially on geometric deep learning, self-supervised learning, generative AI, computer vision, and so on, mostly in biological contexts. And today, Iflai is active within 3 different areas. That's AI for medtech, AI for manufacturing, and AI for security. And I'll show you a couple of different examples from all of these different sectors later on. So some of the challenges of AI today, I'm sure you are well aware, very well aware of these, but I'll go through them quickly anyway. So of course, AI requires typically large amounts of data to train on. That means very high costs for acquiring that data, even if it's synthetic, and maintaining that data. You get very energy-intensive operations, which means you're also dependent on using typically expensive cloud computing. And of course, you have this very labor-intensive manual annotation process, which means that the time typically from when you identify a problem to when you have a solution to that problem, an AI solution to that problem, is at least weeks, if not months, often even years, right? And of course, very importantly, you usually have a very limited EU AI Act compliance due to untraceable data, for instance, via GDPR and the EU AI Act and so on. So the training of AI today can usually be separated into 2 different steps. You usually have some baseline training on a large amount of data, and then to make that solution work for your particular use case, you have a fine-tuning step. And it looks something like this. So again, you have this massive pre-training step where you use a lot of data, tens of thousands of GPU hours of training time, and then you typically expect an accuracy of between 0 to 80% in a new environment that was not included in your massive data set. And to get something to work very well, you add that amount of manual annotations to it. So what we do, really the Iflai innovation in this space, is replacing these 2 things with 2 very, very specific innovations. The first is inductive bias-aware training, where you essentially integrate physical knowledge about the real world into the design of the AI architectures themselves and the training of them before they ever see any data, which means they can reach a very, very high performance with extremely few data points. Sometimes even a single data point is enough to reach optimal performance, and I will show you an example of that soon. And then we also replace the fine-tuning step with something called agentic active learning, where we essentially ask the AI itself which data points in a given data set are the most informative to train on in order to reach the optimal performance. So you don't have to train completely blindly on all your annotations. So what we have today in practice is a toolbox of these inductive bias-aware models that are readily available to solve these tasks. So that's the detection of objects and images, segmentation of objects, so finding their structure, localizing their positions, also in terms of bounding boxes, classifying them, also many forms of generative AI, as I will show you, tracking objects and images, as well as many forms of video analysis and multidimensional analysis. And just to show you one example here is a project we did for a client where they had essentially, it was a biotech firm, where they developed a certain type of surface where if you could track the morphology change and movement of tens of thousands of cells on this surface very consistently over time, you could estimate the risk of those cells being cancerous and estimate the risk of those cells going into metastasis, so being dangerous cancer cells. The problem, though, was that there was no manual algorithm they found that could actually track these cells consistently enough over time in order to develop this into a real diagnostic product. And they also couldn't train an AI. They tried because there wasn't enough data. So we applied our inductive bias-aware models and trained them on 5 data points, and we reached accuracies of above 99.9% in terms of tracking these cells consistently over time. And that number there, 99.9%, is from them. It's from their senior biologist who manually compared against his own tracking of the cells. So the question is, how do we do that? Well, step one is the inductive bias-aware training, right? And here you can see it in practice. Here is the inductive bias-aware training to localize the cells in this particular data set. And here you can see the training happen in real time with no pre-training data in this case, using just a single unlabeled crop of a single image. So this is all the data the model ever trains on. It reaches above 97% accuracy in terms of localizing all these different cells in this data set. And it reaches that accuracy in about 50 seconds of training on a normal laptop CPU. So this is not any fancy hardware or anything behind here. And now that we have this inductive bias-aware model trained, we go to the second step, which is fine-tuning with active learning. So we take this model that I showed you on the previous slide, and we ask it, what are the most informative samples to train on or to get annotations on in order to solve this problem? And usually it'll come up with something like this. So you might have a cell where the boundaries to other cells is very, very difficult to distinguish. Or you might get something like this, where it points out some structure in the noise that very much looks like a cell, for instance. And then what we can see is that within about 15 to 20 iterations, that takes roughly 15 to 20 minutes, you get something that reaches very, very close to 100% performance in this data set. And then looking at another inductive bias-aware model that we used here, we didn't just localize the cells, of course, we tracked them as well. So how do we do that? So here is the result of the inductive bias-aware tracking model trained to track these HeLa cells. You can see they have a relatively complex movement with different splitting events and so on. But actually having just trained this model on a single video of data, that's less than 2 minutes of training time, it reaches an accuracy of 99.2% in terms of tracking these cells consistently over time in this entire data set. But the important thing here is not so much these results. It's that this model actually explicitly tries to estimate the underlying stochastic process that gives rise to this movement. And that's important because it means we can take this exact model and with no further training whatsoever, can we apply it to all other forms of, all the data sets which share the same underlying form of movement. So we can take the same model and apply it to this data set of cells moving. And with no training, it still reaches an accuracy of 99.2% in terms of tracking them. And we can also look at this data set, for instance, where you have more difficult cells that elongate and stretch in different ways, and where the segmentation itself is not necessarily perfect. You still, actually in this case, with no training, you reach very slightly higher accuracy of 99.6% in terms of tracking them over time, essentially by random chance, of course. And then combining these things together, we end up back here. And looking at another client case, there was this case where we used our segmentation model, and this was a microscope manufacturer who essentially sent us a data set of a few hundreds of images containing the most difficult images from their clients. So a very, very diverse data sets with all sorts of biological structures and all sorts of different contexts and so on. And they sent us this data set a little bit as a challenge, a little bit as a joke, because they didn't actually think there was any way of segmenting all these very, very complex, diverse structures at the same time by the same algorithm. Well, we applied our segmentation algorithm in this active learning loop, and after a couple of hours of training, reached segmentation accuracy of about 95% in this case. And that is done with 0 ground truth data to train on. Right? And now we're working on directly integrating this into their microscope effectively. And looking at another client case, we're working on developing a data-efficient foundation model for high-content phenotypic screening for a client in the pharmaceutical industry. So what is that? So high-content phenotypic screening is essentially when you have a large amount of medicinal candidates that you want to test and see which of them are the most appropriate to treat a certain disease, for instance. And it usually looks something like this. So you have some amount of potential treatment compounds or medicinal candidates, and then you take millions and millions and millions of cells in these cell culture plates, and you image them, where you essentially apply all these different medicinal candidates on these cells, and then you image them through high throughput microscopy. And then using some algorithms, usually these are sort of manual algorithms. You segment the cells, you extract the features of the cells, and then from that you get treatment level profiles. So the efficacy of the compounds, the toxicity of the compounds, the mechanism of action in the body, and so on. The problem is that this conventional way of analysis only reaches accuracies of about 15 to 26% today, because the data is just too complex, which means there's a lot of manual quality control involved in these pipelines in terms of screening for new medicines. And well, of course, one would want to replace this whole thing with an AI, so why hasn't anyone done this? Well, there's a lot of papers where people have shown that this is doable and it would lead to very, very good results. But when you actually crunch the numbers, it is prohibitively expensive to train a foundation model for this. There's a lot of data. You don't really reach a good return of investments. So we essentially, let's take our data efficient approach and apply it to this problem and see what a difference it can make. So again, we take this active learning loop, we call it ACL here, and we do essentially everything in the same way. And what happens? Well, here you can see, for instance, the results of unsupervised mechanism of action classification. So if we take one treatment level profile, the mechanism of action, what accuracy can we get? Well, we'll reach an accuracy of 84% in this case, which can be compared with 15 to 26% accuracy today. But more importantly than that are these results, where we show that we reach equal performance to a state-of-the-art AI, but with 10 times less data, which translates to roughly 20 to 30 times less training time, energy, and cost. So now we're working hard with them to scale this up to full industrial scale and include more treatment level profiles effectively. So moving a little bit away from medtech, we can start looking a little bit at the manufacturing examples. And this is one case where we worked for a client in the packaging industry, where in the food packaging industry, where they were interested in detecting bacterial growth in their packages as early as possible. So a little bit of context here is that as soon as they detect that there's bacteria growing in their packaging, they have to throw away the past 72 hours of production in practice, just to be safe, which is of course extremely expensive for them and not very good for the environment. So here you can see the results of our AI after having trained it on a single video from this data set. You can see that, especially looking at the top right video, which is a zoom in on the first detected bacteria, you can see that really as soon as there's a single pixel, a single change in a single pixel there in the middle is detected as the growth of bacteria, meaning that this AI really reaches close to the information limit of how early it's even possible to detect these bacteria given these images in this resolution. And it does this after having trained on one video. And another example, okay, the example's gone. Anyway, it's fine. We're moving immediately to security, where we have developed something called needle in the haystack search together with a client there, where you can essentially search databases of millions of images in less than a second. So one very, very common problem that these clients have is that they want to search very, very, very large databases of images and videos for something extremely specific. It can be, for instance, footage from security camera feeds when you have a network of security cameras. It can also be scanning social media images, for instance, or if they've hacked some particular network of Telegram. It's also a very, very common case. You want to search through a very large space of images. And the problem is doing that today, searching spaces of hundreds of millions of images with the algorithms that exist today takes roughly a couple of weeks. So here, just to show, they gave us this one example where they wanted to find this chair, just to show the power of the algorithm, in a database of about 20 million random images. And here are the results of the search. So you can see actually in the top 8 results, actually the 8th image there in the bottom to the left, you can see that the correct chair is found from a completely different angle, from a completely different room. And this chair is found within 1 second of searching. It can be compared to about 2 weeks it would take with their current algorithm. And yeah, just to show you a little bit that the search itself is generic. You can essentially search for any object. This mountain range that was in the background of an image took about 1.2 seconds to find, for instance. You can, yeah, essentially search anything. And then related to this is this project where you can essentially train your own expert in minutes. So you select any object in an image, and then you find and confirm more AI-identified instances of that object with the active learning copilot. And then a couple of minutes of iterations with this, you can then export and deploy your new lightweight expert detection model that finds exactly that object to essentially any computer infrastructure because they're so small. And just to show you one example of where this has been used, so we worked with a supplier to, for instance, Landvetter Flygplats, who developed these X-ray luggage scanners where you want to detect potential dangerous items in luggage. And they wanted us to compare the performance of our AI to their existing sort of experimental AI. So they have an experimental AI. It's not really used for real because it doesn't work well enough, to be frank. That's been trained on hundreds and hundreds of millions of images. And we were able to show that after having trained on about 100 images, we matched the performance of their existing AI in terms of detecting dangerous goods in a given data set. And we are now involved, among other things, in a tendering offer with them to the Finnish customs, for instance. And then just to show you a little bit here, that of course these algorithms work equally well in multiple dimensions. They've, for instance, been used to study the predator-prey dynamics in a plankton ecosystem, for instance, just to show that. So to summarize then, the Iflai way of training AI is highly data efficient. It requires minimal training data in practice to reach optimal performance. That makes them very cost effective and sustainable. You get very small and energy efficient models that can be run locally in most cases. You get a very, very quick manual annotation done, which means you can go from identifying a problem to getting a solution very, very quickly, even in minutes. And of course, you have the full EU Act compliance with traceable data. And finally, I just quickly want to mention that if you're interested in learning more about how to program these techniques, we are printing a technically focused textbook on AI for data analysis in January next year. It's complete with hands-on programming examples, and all the course material, essentially everything except the book itself, is freely available on GitHub. You can find it via that QR code. So it spans everything from image recognition to language processing, self-supervised learning, geometric learning, reinforcement learning, and so on. And if you want to find the book itself, again, it's printed next month, and it can be found via that QR code. And with all that said, thank you so much for your attention.